Okay, so last lecture we discussed what MLE is and how it can be a tool for solving hypothesis testing problems. Now we are going to deal with a concrete example from the MLE worksheet posted on the course website. Okay, so here is the exact problem statement. Let's go through it. We have two coins. One is green, the other one is purple, and these coins have different probabilities of turning up heads, whereby the probability of getting heads, given that you use a green coin, is 0.9, and the probability of purple coin landing tails up is 0.6. So tail purple is 0.6. And the game is the game master will pull a coin out without looking, flip it in secret, and what you are told is just whether or not the result is heads or tails. And to win the game, you have to guess the color of the coin that he picks up. Let's go through an example run of the game. So at time 1, the game master flipped a coin, and you don't know, is this purple or green? You don't know this, you just know that he has flipped something. And then the result of the flip, however, is told to you. Let's say this guy then tells you the result of the coin flip is actually heads. Now, for the game starts, you then make a guess. In step 1, was purple or green flipped? And likewise, the game could have been such that on step 2, it was tails that was the result, and you still have to guess. Then the question here is, how do we formulate a strategy that will maximize probability of winning? Probability win with a smart strategy. How? Well, good thing we have maximum likelihood to the rescue. Let's reformulate the problem in terms of the maximum likelihood concepts that we have described in the previous lecture. Selecting the problem. Let's see. So the concepts that we have to care about are the data, or the observations, the model, or the guess, and the likelihood functions. I'll call this Ella. So what is the data in this problem? Well, what we are told about is in step 2, whether or not the resulting flip is heads or tails. So let's write this down. As for the models or guesses, we have two choices. We can either guess that the coin that was drawn was actually green, or it was purple. And finally, the likelihood functions. Well, in this case, we just have 4 discrete cases to worry about. As seen here, remember that X is the data that can be heads or tails. So here we have these 4 combinations. Probability of heads given green, probability of heads given purple, probability of tails given green, probability of tails given purple. Probability of heads given green, as we have seen before, is 0.9, which means tails given green is just 1 minus that, 0.1. H given purple, well, we know tail given purple 0.6, so this is 1 minus 0.6 equals 0.4. And ta-da, we have reformulated the problem into a format that we can apply maximum likelihood too. And let's go do just that. So we are going to use maximum likelihood to come up with strategy. So let me remind you that maximum likelihood said we should pick the model that maximizes the likelihood function, and the math is like so. Now, what does this mean? Well, let's break it down case by case. If I have been told that the resulting flip is heads, then let us look at the likelihood functions. Property x of h given theta is green. And let's compare this against when if theta is purple. Well, this quantity we see from, let's see here, that it's 0.9. And this quantity, h given purple, we see here is 0.4. And since the first guy is greater than the second guy, we guess that theta is actually green. And likewise, if we do the same if we receive tails as the observation, we do the same calculation. So I will abbreviate this, tail purple, and we look at our previous numbers. We see that 0.6 greater than 0.1, and so we will guess that purple coin was drawn. Okay, so we did math. Let's summarize our strategy in one line. Strategy: if C heads, then guess green, else guess purple. So a recap of what we did: we just used MLE to come up with this nice strategy. Now then, you might ask, how good is it? The intuition is that if you see heads, right now the strategy says you have to guess green. But what if purple was actually drawn? And the same case for tails, and you guessed wrong. So as you can see, this strategy is not foolproof, and we need some way of quantifying the probability of you winning the game. Now, okay, so what we want is a way to quantify probability of winning. Now, before we do some math, let me give some random variable facts for those of you who have not learned about random variables. The intersection of two random variables can be expressed in terms of the conditional probability times probability of B. And also you can break down a random variable into two mutually exclusive intersections with opposing random variables. Okay, and we'll be making use of these formulas as we calculate probability of winning. Okay, so probability of winning is, we will use the second rule. We are going to break this apart into probability of winning, and the coin flipped was green. Sorry, the coin drawn was green, plus probability of winning, and coin drawn was purple. These two are disjoint events, which is why we can do the summation. And then we're going to use the first rule, where we express the intersection with conditional probabilities instead. Green plus probability of win given purple, probability of purple. Okay, now we just have to compute each of these elements. Let's compute them one by one. Okay, each term. Let's start with the easy one. What's the probability that you draw, that a green coin has been drawn? Well, we assume that the probability is even for both events, so they are just 0.5 each. Now here's the trickier one. What is probability that you win with your strategy, given that a green coin was drawn? Well, to compute this, we don't do more math. We actually do more reasoning. What does it mean to win when? What does it mean to win at the game? Winning means you have guessed the right color using your strategy. So winning here is probability that you guess green with your strategy, given that the coin drawn was actually green in color. And what does it mean for your strategy to motivate you to guess green? That means, let's see, if we look at our strategy, we guess green if we see heads. So this means probability of guessing green, this event, is the same thing as probability that heads was flipped given that green coin was drawn. And we know this value. Probability of H given green, as we can see here, is 0.9. 0.9. Now we'll do the same exercise for probability of win given purple. Winning when purple, that means probability that you guessed purple, given that purple was drawn. And for the probability that you guessed purple, well, again, from the strategy, you guessed purple when you see tails, else when you see tails. Probability that tails was flipped given that purple coin was drawn. And PT given purple is 0.6. Okay, now that we have all of these numbers, let's plug them back into our math formula here. Copy. Okay, all together. Probability of you winning the game is then win divided by green is win on green is 0.9 times 0.5 plus 0.6 times 0.5. This is equal to 0.5 times 0.9 plus 0.6, which is equal to 0.75. Okay, what this means is, if you use the strategy, then you would be winning or guessing correctly 75% of the time. And that is amazing, considering that versus random chance, you would just be guessing where you just guessed green or purple with equal probability. You only have 50% chance of winning the game. So, recap. What have we done in this example? We have used maximum likelihood to derive a strategy where the strategy has winning condition, has probability of winning of 75%, which is greater than random chance. And so we have successfully used math to incorporate all our uncertainties of the data to boost our chances of success.